Here's another fun problem. Let's launch a ball on the ground because we're so good at it. And let's say that we are going to launch a ball um, 20 meters per second at an angle of 10 degrees. So that ball is going to go somewhere. And let's put a little wall over here. Let's put a wall height, let's say 3 meters. Okay, so a wall has a height of 3 meters, and let's put that wall 20 meters away from the ball. And my question is, what happens to the ball? Does it hit the wall? Does it clear the wall? Does it not even know the wall exists? What's going on? Okay, so this height is 3 meters. All right, so what do we do? Same thing. Question is going to be what happens to the ball. Here is my initial velocity because I know that my coordinate system doesn't like that funny angle. So 20 meters per second, and I'm going to break that up into two different pieces, v0x and v0y, and my angle here is, I said, 10 degrees. So v0y is going to be 20 times the sine, because v0y is opposite of the angle of 10 degrees, which is 20 sine 10, 3.47 meters per second. And I'm looking at my picture, it's up, so it's positive, and I'm happy. v0x is 20 cosine 10 degrees, so 20 cosine 10 degrees, 19.7 meters per second. To the right, also positive, so we are happy with that. So we can go back over here, v0 VAT delta x in the x direction and in the y direction. Initial velocity in x, 19.7 meters per second. Initial velocity in y, positive 3.47 meters per second. And accelerations are unchanged, meters per second squared down, and 0. So we end up with 19.7 meters per second, and 0 is the acceleration. What else do we know? These are the ones that are sort of standard if we're given initial conditions. Now we have to think about what we're asking. Really what I'm asking is, because we know that this ball is going to fly, I want to know, does it get over the top of this wall or not? I want to know how high the ball is when it has traveled 20 meters. So I am going to let the ball travel 20 horizontal meters. And I'm going to use that information to calculate the height. The height could be up here, higher than 3 meters, or the height could be lower than 3 meters. So I'm looking for what's going on in this plane right here, right? What happens when the ball's traveled 20 meters? What's the height? So I know everything I need to know for the x column, so delta x is equal to v0 t plus 1/2 a t squared. Acceleration in x is 0. 20 is equal to 19.7 t, or t is equal to 20 divided by 19.7, 1.015 seconds. So I can say time to get, this is time to go 20 meters, so how much time it takes to get to the wall is 1.015 seconds. 5 seconds. I'm going to share that time because I want to find out how tall is the ball. What's my delta y? What's my delta y right here when the ball has traveled 1.05 seconds? So delta y v0t plus 1/2 a t squared. Delta y is equal to 3.47 times 1.015 plus 1/2 times negative 9.8 times 1.015 squared. And those are all numbers. So 3.47 times 1.015, 3.52 plus 4.9 times 1.015 squared minus, because of this negative sign here, so minus 5.0405, 3.52 minus 5.05, negative 1.53 meters. What does that mean? Negative 1.53 meters. What does that mean? That means when the ball has traveled to this 20-meter line, what's the height? The height is negative 1.53 meters. How could that possibly be? It's right here. What does that mean? That means the ball, if I want to draw on that path, goes up and falls down. It means it gets negative 1.53 meters when it's gone that far. These equations don't know that the ground is there, right? So you're thinking, well, how can it go underground? Well, in effect, it doesn't. It doesn't really go underground. But what it does is it lands right there. So, does it clear the ball? Does it clear the wall, I mean? No, the ball doesn't go over the wall. The ball lands in front of it. And if we're interested in figuring out where it lands, then we have to set up new columns of variables and say, well, it lands in front of the wall, so now we can just look at just this part of the problem, right? Just this part of the problem right here, and it looks like a standard flat problem, which we know how to do and we're almost bored to death with. So we won't do that, but the question could be, oh, what happens if it lands right there? Where does it land? By finding out that the delta y is negative, it means that it's hitting down below, which means it actually lands in front of the wall. Let's change our parameters a little bit. Let's do the same problem, but let's shoot it up higher in the air. So let's take our ball and let's shoot it up 20 meters per second, same speed. And let's shoot it up higher, because from our lab we know that the higher things go up into a certain angle, it's going to go farther. Let's shoot it up 30 degrees, right? Let's still put our 3-meter tall wall, 3-meter high wall, out here 20 meters away, right? So everything else is going to be the same. We're going to still look for what's the height here. Let's see if this clears the wall. So what changed? Our initial parameters changed. Now we have 20 meters per second, and we have an angle of 30 degrees. So my V0x, V0y, x, and I've got 30 degrees instead of 10 degrees. So my V0y is equal to 20 sine 30. And 20 sine 30 is equal to 10, and 20 cosine 30 is equal to 17.3. So this is 10 meters per second. V0x is equal to 20 cosine 30, which is equal to 17.3 meters per second. We can go back and say x and y. So notice I'm really just doing the same problem, and we're going to see if it changes by making this steeper. So V0, VAT, delta y. We can still see all that. So in the x direction, 17.3 meters per second, 10 meters per second, negative 9.8 meters per second squared, 0 meters per second squared. And again, I'm going to look for what happens at 20 meters. I'm still looking for this 20-meter line. How much time does it take to get there? Delta x is equal to V0t plus 1/2 at squared. Acceleration is 0 in the x direction. 20 is equal to 17.3 t. T this time is equal to 1.16. So because it's steeper compared to up here, it's in the air longer. So time is equal to 1.16 seconds. We can share that. What happens? Where is the ball when it is 1.16 seconds in the air? So we can go over here and say delta y equals V0t plus 1/2 at squared. is equal to 10 meters per second times 1.16 seconds plus 1/2 times negative 9.8 times 1.16 squared. So we get 11.6 minus 4.9 times 1.16 squared minus 6.6. So we get 5 meters, right? 5.0 meters. And so we can look and we say, look, delta y is 5 meters. In this case, our wall was 3 meters high. The ball goes like this. And it is a height of 5 meters, which means that it is 3 meters for the wall and another 2 meters clearance. So the ball goes over the wall and there's 2 spare meters of clearance. So we have just hit a home run or kicked a field goal or whatever the proper sport would be. We've served the ball over the net. Okay, you get the picture. So we notice that changing the angle makes the ball go farther, but in both cases we're using the 20 meters to figure out what's happening at this point.